guys. I think yesterday we had a power outage.
We had like 3.
Was that?
We had like 3.
Oh, really?
We were in lab and it kept going. The lights kept going on.
Kept going on. Okay. So that means that I don't have access to that. So I'm just going to go off notes. Jenna was kind enough to give me hers. We're in chapter 17.
Yeah.
And I think we were just going through buffers.
Henderson,
Page
Hasselbeck.
6. Is it the same thing?
Page 7. So we got right to Henderson Hasselbeck, I think?
Yeah.
Okay. So please, I'm going to start here. So I think we briefly talked about Henderson Hasselbeck, right?
Yeah.
That's just pH equals pKa plus the log of the base over the acid, I think it was.
Yeah.
Right, so I'll just do this, base over acid. That's the simple form, right? Yeah. Okay. Now, we're talking about buffers, and here's what we're looking at. Up to now, if you were looking at a buffer, how would you determine the pH? Let me start with that.
Negative log of the hydronium or the hydroxide.
You would find the Ka
Right.
or the Kb, if it was given, and you set it based on an ice chart if you had some early information about one or two of the reactants or products, right? And then you set the Ka or the Kb, depending, relative to the concentrations that you have on those with X, minus X, whatever you had, right? Use the ice chart. And then if you had OH minus or H3O plus, that's where you're setting the Ka or Kb to, and then you determine what X was, and then from that you plug it into negative log, and that gives you the pH, right? If it's the hydronium, or POH if it's the hydroxide.
Right.
Everybody following me on that? So here I'm saying, well, let's say I have the Ka, and I know the concentrations, which I may have to figure out, by the way, in some cases using ice anyways. But if I know the initial concentrations of the base and the acid, I could convert the Ka to pKa, and I could solve for the pH. An easier way to solve for the pH. Two things to think about, though. One is, when I'm looking here, I'm talking about the initial concentrations here. And then I'm saying I'm using the pKa. Does that make sense?
Mm-hmm.
Does that make sense? Does that statement make sense? What is the Ka? Are those initial concentrations or those equilibrium concentrations?
Equilibrium.
Equilibrium. So then the first question would be, then why can I use initial concentrations? Okay, that's what I want to point out, because that's what makes this equation a little bit tricky, right, when you think about it. And what would be the rationale? Let me ask this.
Over the ratio?
Would I use this equation for a strong acid?
No.
No, why?
All the equals.
And is it easy to figure out what the pH is on a strong acid?
It's a ratio of 1.
Yeah, you just follow the stoichiometric ratio in a balanced chemical equation, right? So then if it's a weak acid, why can I usually use this equation to figure out the pH even though I'm using the initial concentrations here?
Because you have the pKa?
I have the pK, which is relevant, but what about the initial concentrations compared to the equilibrium concentrations?
It's weak, so they don't change that much.
They don't change that much. They're almost the same, right? The value of that is very small. The same way you can get rid of X when you take the initial minus X, and then you just make the, what do we call that? What is it?
Negligible.
It's negligible, but we called it a certain rule.
Approximation
Rule, right?
Right.
And we just did that. Once again, you don't have to necessarily know that term, but that helps you remember what we've already covered and why this is insignificant or negligible. So I could use the initial concentrations here to figure out the pH if I know the Ka, or I can convert the pKa, okay? I think the one thing you guys had in lab that I pointed out is you could also look at the POH here. Okay, and that just equals the pKb plus log, and here you're just taking, and I'm not requiring this, but the acid over the base. Okay, that's just an alternative way to do the same thing. And did that help you guys, by the way, in lab when you did this?
Yeah.
Did some of you use that? I know that you were asking about that. Did that make it easier to solve for what you wanted to solve for?
More sure, yeah.
It did?
Mm-hmm.
Okay.
Give me the
And if it doesn't, don't use it. And if you want, use it. You'll get, if you do it, you'll get the same thing. By the way, if I got the POH and I wanted, if I had the PKB and I didn't want to make all the conversions, which would just KW divided by KB would give me the KA, right? PKA. So if I wanted to make the conversion and I just solve for this way, then I just take 14 minus this to get this, right? There are all kinds of different ways to do it. So you could do them all solving just for this. You don't ever have to use this. But if you wanted to, you could use this and then do the 14 minus at the end. It's just an alternative way to do it. Okay, so this is the Henderson-Hasselbalch equation. Okay. Let's see, they have a example here. Is that what this is next?
Yes.
Okay, a couple things I'll point out. So since I don't have this up and I'm not going by slides, I don't want to go too far off, but I kind of want to, it gives me some variability on how I approach it. If I were looking at this, what I would do, right? And how I would think about this or learning this. The first thing I'm going to say is that generally you want your pKa to be close to your pH. That creates a better buffer. It also means that this ratio here is going to be close to the same. The closer to this, if this is 1/1, that makes this what?
0.
0, which means that my pKa equals my pH. That's usually in that range is the best range for a buffer. Because what am I looking at? So if I'm going to use a buffer, I'm going to put some things into that buffer. And ultimately, I'm going to put something that's going to change that pH. So that means that whatever I'm putting in there, I probably have some kind of a reaction that's going to occur. And that reaction needs to occur around a particular pH. So I want to set my buffer in the range of the pH that I want the reaction to occur. Okay, I want to put this in context because this is much more relevant. All the book's going to tell you is simply that I want to make a pH of this, but why? And I'm saying, I gave you an example before because that's what I did my graduate work on, transcription initiation, right? Everybody knows what that is?
Yeah.
Taking the DNA, taking polymerase, it binds to DNA, at least in a prokaryotic, a very simple system. You have the hollow enzyme with the sigma that binds to the -10 and the -35 region to the DNA. It melts the DNA and you transcribe that non-template strand into RNA. Okay, that's a prokaryotic system. It's much more complicated with histones and nucleosomes and eukaryotic systems. Okay, so that occurs under certain pH conditions more optimally than others, and it may not occur at all in certain conditions. Why?
pH, or they're not.
What would the pH do though? Let's say I had it really acidic. What could that potentially do in terms of the polymerase and the DNA and the interaction and the actual enzymatic activity? Denature. Heard a couple. That should be pretty common. Potentially the proteins aren't natured properly. Why? You have sulfur bonds, disulfide bonds, different things that are holding the protein together, which is in different subunits. You also have a certain pH that holds the DNA together, double-stranded. Then, under optimal conditions, they're both at the most, prime conditions for it to bind, and then it could have its enzymatic activity and activate. So let's say that pH randomly is 6.4, and it's not that. Let's just assume that in this case. Then I want to make a buffer that is close to this. Because when I put something in, I may put something in that has a little bit too much acid or base in it, and that would change this. So if I have a good buffer system, which means that I find the buffer system close to pKa to 6.4, then when I put everything together, and let's say it becomes a little more acidic, this maybe only moves up to 6.5. And it's still a good system to now go ahead and do my reaction and see what happens.
So in a way, blood serum has a buffer itself?
Well, I like that question. Never heard that. The question was, in blood, is there a buffer?
Oh, yes, bicarbonate.
Bicarbonate.
Goes back and forth.
Remember, and I brought that up in 101.
101, yeah.
It was 102, 101. What is bicarbonate?
H2CO3.
H2CO3, bicarbonate, HCO3 minus. If it's too acidic, that means I have a lot of these. This can pick it up and reduce that acidity. Okay? If it's too basic, a lot of these, this can come off and reduce the basicity. Does everybody see that? So absolutely, this is the buffer system, essentially, for blood to regulate the pH.
So that's what hemoglobin is doing too, it's regulating the oxygen?
Hemoglobin is a little bit different. That's bringing in O2
Right.
through the system into the lungs, and then that's being released under certain pH conditions. So the pH does matter for that. And then it's picking up the leftover and taking it out. So when the pH is going to control the structure of the enzyme. I think it's quaternary, so it has four different pieces.
Iron
And it forms a middle piece,
With the iron.
right, with the iron. And they're, under certain pH conditions, it's optimal for picking up the O2. Then as it transfers through to where it's going to release them in the lungs, those conditions are now changed in terms of the pH, which is why it releases it and now picks up the leftover and brings it back over, which is why it releases there. So the enzyme itself changes as a result of the pH through that process. Okay? And that's how it's optimized to pick up O2 and release O2 at those different time points or different positions within the cells. That make sense? And if you're at a higher elevation, there's also a few other things associated with that. I think there are different proteins that get insert in the middle to stabilize it or whatever, 2,3-BPG or something like that, if I recall. So there are different conditions that allow for the system to do this or not. And this is an example. So now if I'm creating, by the way, in vitro, in vivo. In vitro means I'm taking things out of the cell, out of cellular content, and I'm testing them. In that case, I need to have a buffer. And that buffer ideally is going to represent what? What would be the ideal buffer situation?
One or two of those.
Similar to what it's like in the cell.
Okay.
So then I'd break open some cells, assess what the conditions are like in terms of the salt conditions, pH conditions, and other things. And then I mimic that in my buffer solution. And then I put in the two different components, say polymerase and DNA, and then I see if it transcribes, if it binds, if it melts, or whatever it is I'm looking for. Okay? So then designing the buffer system is not, so all we're doing and all the textbook does is say, okay, I want a close I'm just explaining this, here's the pH, I want a close pKa so that it doesn't fluctuate much. And the whole point of the buffer is so that you don't fluctuate much. What I'm doing is I'm trying to put it in the context of where it would be useful. Why do I do this? Why do I care about this? Right? And so I'm saying, I want to create the pH to optimize whatever it is I'm looking for, is usually in vitro, because in vivo is just doing things within the cell itself. Okay? And then to do that, I'm going to look at the pKa and get it as close to the pH as possible. So that means that whatever my base and my weak base in conjugate acid or my weak acid in conjugate base has got to have a pKa close to the pH I want. That's how I'm determining what system I'm using. I may not have one that's right at that pH, obviously. So then I could only choose systems that are as close to it as possible. Does that make sense? Then the amount of the conjugate base and the weak acid, or inversely, should be as close to each other as possible so that this is limited in the scope of how much it's going to fluctuate the pKa value if I have a pKa value close to the pH. And presumably I'd rather have that at +1 or -1 difference. Beyond that, then it's going to start to have too great of a change of what I want the pH to be. Okay, and if you're not sure which way to go, you could always plug in numbers, the same thing I keep saying. So if I have the weak acid and its conjugate base, and this is going to take the peak with the pKa, which is not usually going to be exactly at the pH, obviously, hopefully close, and it takes it too far away from the pH, then I need to make an adjustment on one of these in order to get it closer to the pH I want. So even if this isn't exactly at the pH, let's say this is I want 6.4 and this is, say, 5.9. I could play around with this adjustment to make that closer. But then I also have to worry that if I put in an acid or a base, am I making this too far off so that I would use up all of one or the other, and then that would jump the pH a lot, right, once I've used it all up. Which also should say that the concentration of each one of these matter as well. If it's too low of a concentration and I put a certain base or acid in, it's going to use it all up, and then it will just cause the pH to drop or go up significantly depending on what I put in. So those are the dynamics at play with determining a buffer. Using the Henderson-Hasselbalch equation allows you to assess all of these things and create potentially the best buffer system for what you're trying to accomplish. So, did you have something for me? You want to turn this on?
I need time.
Okay. If you need, just let me know. Okay. Thanks, by the way. Okay, so are there any questions related to this? Go ahead.
When you said something needs to be +1 or -1, what?
So if I were to make this became +1, that would take it 1 unit beyond the pKa, and that adjusts. So I want the pKa to be +1, -1 for. So let's say I want the pH 5. Then I wouldn't want this to be greater than 6 or less than 4. +1, -1 from that. Go ahead, Ruben.
If you're given a pH, or you need to make a buffer system given whatever pH, whether it's acidic or basic, would there be an importance of choosing a weak acid conjugate base? Or
Yes, and that would be
base?
its pKa. That's where the pKa comes in, right? I want this as close as possible to that pH that I want.
Okay, because there was a post-lab question on the labs itself that it asked us for whatever pH it was 6, 8, and 11, and it's only telling us to look under the weak acid conjugate base option. It didn't actually let us go into the weak base.
That's okay, so then you just look, if you have that, you look at that and you say, what's gonna get me the closest to this?
Okay.
And then I want this to be as close to 1 as possible.
Right.
So if this could be 0.1 and 0.1, that's great. If it's 0.9 and 0.8 or whatever, then that's going to adjust it. And I may want to do that to get this overall closer to the pH. But then remember, when I put something in, now that's going to change it.
Right.
But if I have all these things set up properly, then it's not going to change it a lot. And we'll take a look at the fluctuation and change by using different pHs and different concentrations and other things. Alex?
I have a question.
Oh, Jenna?
So basically, what you're saying is that the log B over A should be between -1 and
+1.
1. And if it's greater or less than that, what happens?
Well, then I might be outside the range of what I want to accomplish with the pH. And now when I put something in, it goes one way or another, it's not useful anymore. It's not a good buffer for the system I want to use it for. It may be a good buffer for something else.
Right.
But for what I want it for, it's not good. It's not optimal. But if, hey, when you're doing research and you have certain things available to you, you may not have anything that available. So if you had to go outside of that just to get as close of something as what you want to accomplish, then you would have to. It's just not an ideal situation. It doesn't mean you can't use it, right? And if you use it, you might want to then make you make a greater adjustment here. One way to do that is just by adding a higher concentration of them. So, so if I put, say, 0.5 and 1.0 molar here in order to get this closer to the pH I want, but then I put in something that would use up all that 0.5, then it's no good. So one way to do that, and since this is maybe outside, then maybe I make this, 1.5 molar and 2 molar to get the ratio I need to get the proper pH, and then not all of it will be used up. Remember that one chart I showed you where the HA goes up and the other PA goes down, or inversely, or whatever. Then I have enough to maintain the conditions in the reaction that I'm trying to do. Mm-hmm. So you can go outside of it, but you prefer not to if possible. Okay, so let's see now. Yeah.
So if a question is asked, let's say it gives you a certain pH and it says, is this within the acceptable range? Should we assume the range is always +or -1?
Yeah.
Yeah. In all the questions.
Yeah. For this class, yes. Once again, when you're now, and I love to state this, and I do it often, but I know that some of you pick it up and